Hello, I'm audible.
Yes, sir.
Okay. Screen is visible.
Yes, sir.
Right. So yesterday we have started the module number 3, beams on elastic foundation. So yesterday we have derived one basic equation for the deflection and the stress, delta and Q, right? Sorry, delta and sigma xx, delta and sigma xx, that is deflection and the stress that we have derived in last lecture. Now again, beams on elastic foundation, that is classification of the beams on elastic foundation. So before that, below the foundation soil mass is considered as identical and independent and closely spaced linearly elastic springs, which is known as wrinkle foundation. So we have to use this concept in case of the beams on elastic foundation, right? So what is wrinkle foundation? You can see here, this is the beam, okay. Then x-axis, z-axis, and W is nothing but your pressure, which is acting. And this is a wrinkle foundation. The load is acting, that is concentrated load is acting on the beam. So pressure is exerted on the foundation from the soil which is below the foundation. As we have discussed elastic foundation in last lecture, right? So this is nothing but your elastic foundation and this is your wrinkle foundation, right? For analysis, we have to consider this concept, that is wrinkle foundation concept in case of beams on elastic foundation. So reaction pressure is nothing but Pw is equal to K naught into W. W is nothing but the pressure which is acting. K is nothing but the foundation constant. Okay. K naught is the foundation modulus. Okay, floating on liquid, that is buoyancy force. So K naught, that is foundation modulus, equal to lambda liquid. Okay, that is density of liquid is equal to G into mass density, that is rho into liquid. The reaction force intensity, that is reaction force over the unit length, then QW is equal to minus K naught BW is equal to minus KW. So minus K naught B is nothing but K. So where B is the width of beam and K is the foundation constant. This we have to consider in a wrinkles foundation. So this we have to consider in case of beams on elastic foundation, that is wrinkle foundation. The beneath the foundation soil mass is considered as a identical. जे बीमच्या खाली जे फाउंडेशन सॉइल आहे, below the beam, whatever the foundation soil mass is there, which is considered as identical, independent, closely spaced, linearly elastic springs, which is known as wrinkle foundation. That foundation we have considered as a Winkler foundation. Okay, whatever the soil which is below the beam, that is identical, independent, closely spaced, linearly elastic springs. It is behave like springs, which is known as Winkler foundation, that we have to consider in case of beams on elastic foundation. So whatever the bending of beams on elastic foundation, whatever the bending of beams on elastic foundation is developed on the assumption that whatever the bending of beams on elastic foundation is developed on the assumption that the reaction forces of the foundation, as we were discussed in last lecture, right? The reaction forces is proportional at every point of the deflection of the beam at that point. Yesterday we have discussed Q is directly proportional to the delta. Q is directly proportional to the delta, that we have discussed in last lecture, right? So in case of the elastic foundation, that we have considered the assumption that whatever the reaction forces on the foundation, which are proportional at every point to the deflection. And one of the most important deficiencies of the Winkler foundation or Winkler model is that whatever the displacement, discontinuity appears between the loaded and unloaded part. Right? The displacement discontinuity appears between loaded and unloaded part of the foundation surface. And in reality, the soil surface does not show any discontinuity. But we would assume that, right? So this is the classification of beams on elastic foundation. The beams on elastic foundation can be classified into three types. Beams on elastic foundation can be classified into three types. Okay, one is short beam, second is medium beam, third is long beam. Short beam, medium beams, and long beam. Okay, medium beam is also called as infinite beams, and long beam is also called as finite beams. Remember, in the question paper, right, the question may be asked that is the define the classification of beams and derive the basic equation of the reflection and the stress sigma xx, that is we have derived in yesterday's lecture, or maybe the equation for semi-infinite beam subjected by the concentrated load at the center, or the moment, or the equation for the infinite beams for the concentrated load or for the UDL, etc. So in this module, the question will be asked in the exam. The questions will be asked in the exam based on this semi-infinite beams, infinite beams subjected by concentrated load, UDL, or the moment. Okay, that is derivations. Derivations will be asked in the exam. Okay, on this model. So beams on elastic foundation can be classified into three types. One is short beam having beta L. Yesterday we have taken the value of beta in terms of K and EI. Right, beta L less than or equal to 0.6, where L is the length of the beam, So beta L less than or equal to 0.6, then it is called as short beams. If beta L is in between 0.6 to 0.5, means greater than 0.6 but less than 5, then that is called as medium beams or semi-infinite beams, right? When it is called as semi-infinite beams on elastic foundation, when beta L ratio is greater than 0.6 and less than 5. And last, long beams or infinite beams, that is beta L is greater than or equal to 5. When beta L ratio is greater than, sorry, beta L is greater than or equal to 5, then that is called as a long beams or infinite beams, right? Where L is nothing but the length of beam. Remember this, the classification of beams on elastic foundation: short beam, medium beam, or semi-infinite beam, or the long beams or the infinite beams, right? So now infinite beams which is subjected to the point load. Okay, beam which is subjected by the point load. So if you consider the long beam, if you consider the long beam, point load is applied, that is nothing but suppose P, right? Point load is applied, that is suppose P. Q, Q is nothing but your reaction. Q is nothing but the reaction, right? So which is acting at the bottom of the particular beam. Okay, below the beam there is a foundation. So whatever the pressure or the reaction from the foundation which is acting at the bottom of the beam. So if you're taking the segment, this small segment, right? We have to consider this small segment having width is your delta Z, having width is your delta Z, right? Now we have considered this small portion, okay, that particular beam portion, okay, at that particular section, okay, it is subjected by the moment mz, as we were discussed in last lecture also, mz, okay, and on this side there is for small element the moment is your delta mz, then the pressure or the reaction is acting on upward side, okay, q into delta z, shear force vy plus delta into Vy, that is small for small segment. Okay, Vy is nothing but the shear force which is acting on the surface of that particular segment. So we have to consider the equation from the bending theory. EI d2y by dz square is equal to minus m. EI d cube y by dz cube is equal to minus y. Sorry, minus V, that is shear force, and EI d4y by dz raised to 4 is equal to minus Q. Okay, so these are the general equations for bending moment, shear, and the reaction or the load. Now, where the distributed reaction force Q, which is from the foundation on the beam. Okay, when the distributed reaction force Q is positive, when it is acting in upward direction, Q is a positive when it is acting in upward direction. So for linearly elastic foundation, the distributed force Q is linearly proportional to the deflection Y, or you may call it as delta. Okay, we have discussed in last lecture, Q is directly proportional to delta, right? So you may call it as also delta, that is deflection. So Q is linearly proportional to the deflection delta. So Q is equal to K into Y, where K is nothing but the elastic coefficient. K is nothing but elastic coefficient. And as per the Wrinkle's foundation or Wrinkle's model, K is equal to B K naught. As per the Wrinkle's model or Wrinkle's foundation theory, K is equal to B K naught, where K naught is the elastic foundation modulus and B is the width of the foundation. Okay. Q is directly proportional to the delta. Proportional constant is taken as K, that is called as elastic coefficient. And as per the Wrinkle's model or Wrinkle's foundation theory, K is equal to, that is elastic coefficient K is equal to B into K naught, where K naught is the elastic foundation modulus and B is the width of the foundation or the width of the beam, right? So now, you know these equations, we have to use these equations. So putting the value of q in this equation, EIX is equal to d4 by y by dz4. You may call as IX or IZ. D4 delta, as we have discussed in last lecture, dx raised to fourth is equal to minus k into delta. Right? Yesterday we have discussed this. So AIX or AIZ d2 d4 raised to y by dz raised to 4 is equal to minus ky. So k EIX is on this side, k by EIX into y. To solve this homogeneous and fourth order linear differential equation, okay, to solve this homogeneous fourth order differential equation, so we are assuming that k by EIX is equal to 4 beta raised to fourth. We are assuming that k by EIX is equal to 4 beta raised to 4. Then we get the equation is equal to d4 raised d4y by dx4 plus 4 beta square y is equal to 0. So by using the method of differential equation solution, okay, we have we get this equation, right? Now putting the boundary conditions, since the deflection delta is equal to 0 or y is equal to 0, so z is infinity, then the term e raised to beta z tends to infinity and e raised to minus beta z tends to 0. Okay, by putting the boundary conditions, then whatever the constants C1, C2 is equal to 0, so we get this equation of deflection. We get this equation of deflection y is equal to e raised to minus beta z c3 sin beta z plus c4 cos beta z. Okay, this is the equation of your y or the delta. We have given the putting the boundary conditions, etc. So by putting the boundary conditions, we get the equation that is C1, C2, 0. So deflection is equal to 0. Sorry, deflection delta is equal to e raised to minus beta z, C3 sin beta z plus C4 cos beta z. So again, by using the boundary conditions, as dy, first boundary condition that we have to put as dy by dz is equal to 0 at z is equal to 0. So we have to differentiate this equation with respect to z. We have to differentiate this equation with respect to z. So dy by dz is equal to minus beta e raised to minus beta z c3 sin beta z plus c4 cos beta z plus beta e raised to minus beta z c3 cos beta z minus c4 sin beta z, which is equal to 0. So we get c3 c4 is equal to c. So we get the equation of deflection. We get the equation of deflection delta or y is equal to c into e raised to minus beta z sin beta z plus cos beta z. This is for first boundary condition when dy by dz is equal to 0 at z is equal to 0. Okay, we have to differentiate with respect to y. Okay, sorry, we differentiate with respect to z to this equation of y. So we get this final equation for the first boundary condition, y is equal to c e raised to minus beta z sin beta z plus cos beta z. Now second boundary condition, that is 2 into integration of 0 to infinity ky dz is equal to p right? P is nothing but the concentrated load is there. P is nothing but concentrated load. So we have to put the value of y here. We have to put the value of y, that is C into e raised to minus beta z sin beta z plus cos beta z, okay, dz. So we have to integrate, and by putting the limit 0 to infinity, so we get the value of c. We get the value of c is equal to P beta by 2k. P is nothing but concentrated load. Beta is the that value we have taken constant in terms of k and ei. Then k is nothing but the constant of elastic foundation. So C we get, that is constant. C is equal to P beta divided by 2k. So the equation of deflection, that is delta or y, because previous equation we know that this equation of y. So here we have to put the value of c. Here we have to put the value of c. So we get the equation y is equal to p beta by 2k e raised to minus beta z sin beta z plus cos beta z, right? So dy by dz slope theta, right? Rate of change of deflection is we get the slope. Rate of change of deflection we get the slope. So dy by dz is equal to theta, that is slope. So whatever the equation of y, that we have to differentiate taking the derivative with respect to z. Whatever the equation, previous equation of deflection, whatever the previous equation of deflection, that we have to differentiate with respect to z. So we get the equation of theta, that is slope, is equal to minus p beta square by k into e minus beta z e raised to minus beta z sin beta z, right? Now we get the equation of slope and deflection. Now we have to find out the equation of moment and the shear force. So mx equation is known to you from the bending theory. Mx is equal to minus EIX d2y by dx dz square. So as we know the value of y, that is deflection in terms of load, and k, so putting the value of y and taking the derivative two times. So after that we get the moment equation mx is equal to p by 4 beta e raised to minus beta z cos beta z minus sin beta z, right? Next, equation of shear force, rate of change of bending moment. Equation of shear force, rate of change of bending moment. So minus dm by dz. So take the derivative of equation of moment with respect to z. So we get the equation of shear force Vy is equal to P by 2 e raised to minus beta z cos beta z, right? So these are the equations of your deflection, slope, moment, and shear. Okay. These are the equations of your deflection. Y is nothing but deflection, theta is slope, moment m, V is shear force, right? Now in the equation of y, in the equation of y, in the equation of slope, in the equation of moment, in the equation of shear force, you can see here equation of y, p beta by 2k e raised to minus beta z sin beta z plus cos beta z. So in the equation of y, so e raised to minus beta z cos beta z plus sin beta z, right? That it is considered or assumed as a beta z. This term is assumed as A beta Z in the equation of deflection for simplification only. Then in the equation of slope, this is again B beta Z. In the equation of mx, this term is taken as C beta Z. In the equation of shear, this term is taken as D beta Z. Okay, that is for simplification. You can see here, right? These terms are taken. So y deflection is nothing but P beta 2k A beta Z, theta is minus P beta square by K B beta Z, mx is P by 4 beta C beta Z, and shear force Vy is equal to P by 2 D beta Z. Okay, for simplification only, right? Understood? Yes or no? What we have discussed in last lecture that I have revised once again. Understood? Anyone having difficulty? No. So can you write the equations of this deflection, slope, theta, and moment and shear? Equation लिहून घेता का?
Yes, sir.
Okay. So write down the heading: infinite beam subjected to point load. Or you, okay. Classification notes सर देना रहे, ठीक है? Write down infinite beam subjected to point load. Infinite beam subjected to point load. Write down infinite beam subjected to point load. Write down infinite beam subjected to point load. Then write down this equation of deflection. You may call delta or y. Write down deflection, equation of deflection. P beta by 2k e raised to minus beta z sin beta z plus cos beta z. Y is equal to P beta by 2k e raised to minus beta z in bracket sin beta z plus cos beta z. Over, shall I proceed?
Yes, sir.
Right. Then equation of slope theta. Then equation of moment. Then equation of shear. Slope, moment, and shear. Please write down these three equations. Is it over? Shall I proceed?
Yes, sir.
Yes, sir.
Okay. Then write down this. Write down this. Okay, for simplification only, we have taken these terms A beta Z, B beta Z, C beta Z, D beta Z. As equation is with you, only for simplification, we have taken these terms. So write down these terms and write down then rewrite down the equation of deflection, slope, moment, and shear. Please write down these equations. Yes, over. Is it over? 'Shall I proceed?
Yes,
Yes,
sir.
sir.
Okay, 1 minute. 1 minute. 1 minute. Okay. Is it visible?
Yes, sir.
Okay. Just for a calculation purpose, we are taking one numerical. Take down first numerical. Take down first numerical. Then a railroad uses. Down. A railroad uses steel rails. Down. Railroad uses steel rails where modulus of elasticity is equal to 200 GPa. with a depth of 184 mm, with a depth of 184 mm, full stop. The distance from top of rail to its centroid is the distance of top rail to its centroid is 99.1 mm. Distance from the top of rail is to its centroid is 99.1 mm. And moment of inertia of the rail is moment of inertia of rail is moment of inertia of rail is 36 into 10 raised to 6 mm fourth, 36 into 10 raised to 6 mm fourth, full stop. The rail is supported by ties, ballast, and road bed. The rail is supported by ties, ballast, and road bed that together are assumed to act as elastic foundation, to act as elastic foundation, to act as elastic foundation with modulus of subgrade reaction K, with modulus of subgrade reaction K is equal to 14 Newton per mm square, 14 Newton per mm square. Length of beam is 6 meter, or length of foundation. Length is 6 meter. Next line, only we have to consider first only. Next line, determine the maximum deflection. Determine the maximum deflection, that is y or delta. Determine maximum deflection, maximum, word is maximum, maximum deflection, comma, maximum bending moment, maximum bending moment, maximum flexural stress, maximum bending moment, maximum flexural stress, stress m by I into y. त्यासाठी तुम्हाला सेंट्रॉइडचं y दिलेला आहे 99.1 mm. M by I is equal to F by Y, right? M by I is equal to F by Y. त्यावरून तुम्हाला F फाइंड आउट करायचं. M माहित असणार आहे, मोमेंट I माहित आहे, Y सुद्धा दिलेला आहे. Okay, find out maximum bending moment and maximum flexural stress in the rail for a single wheel load of 170 kilonewton of 170 kilonewton, wheel load of 170 kilonewton, wheel load of 170 kilonewton. Is it over?
Yes, sir.
Is it over?
Yes, sir.
Right. Okay, now please draw this diagram first. We have taken the origin here where the load is acting. This is Z axis, this is your Y axis, right? So this is, we have taken the origin where the load is applied at that particular point, value of Z is 0. So please draw this diagram. Okay, it is continuation, it is beam, and below that there is a foundation. Whatever the hashing line is there, these are nothing but foundation. Please draw this diagram. Diagram is over. Diagram is over.
Yes, sir.
Okay. So first we have to find out the beta. So we know the equation of beta. Look here. Write on this equation. K by EI is equal to 4 beta raised to fourth. Write down this equation. K by EI. K by EI is equal to 4 into beta raised to 4. Write down this equation. As in each term there is a cos beta, sin beta, z, etc. So we require the value of beta. So write down k by ei. K by ei is equal to 4 into beta raised to 4. 4 multiplied by beta raised to 4. So beta is equal to fourth root k divided by 4 ei. So beta is equal to fourth root of k by 4 ei. K by 4 ei. Beta is equal to fourth root of k by ei, k by 4 ei. So we know the values of k and ei, which is given in the equation. K is 14, E is 200 GPa, and I is 36 into 10 raised to 6. So put the values and check whether it is correct or not. Beta is equal to 14 by 4 into 200 into 10 raised to 3. That is 2 into 10 raised to 5 into 36 into 10 raised to 6. Put the value and check whether it is correct or not. Calculate the value of beta and check whether it is correct or not. 0.000835. Is it correct? Yes, is it correct? Value of beta? Please do the calculation and check whether it is correct or not.
Yes, sir. Correct.
Okay. So unit is mm raised to minus 1. That is 1 by m, 1 divided by mm. So next we have to find out beta L. Length is given, beta into L. So multiply by length of beam or foundation. That is 6. We get 5. Check. It is 6,000. You make multiply by 6,000, huh? Because 6 meter is there, that you have to convert in mm. So multiply by 6,000. Check whether it is 5. Get cancelled. 1 by
Yes,
and
sir.
mm.
5.
5 बरोबर है?
Yes, sir.
Right. So next line, add on. For the maximum deflection and for maximum bending moment, add on. Maximum deflection and the maximum bending moment. Maximum deflection and maximum bending moment occurs below the load or under the load. लोडच्या एक्झॅक्टली खाली आपल्याला बेंडिंग मोमेंट मॅक्झिमम भेटेल और द डिफ्लेक्शन. Maximum deflection and maximum bending moment occur under the load where Z is 0 because it is origin लोडच्या एक्झॅक्टली खाली आपण ओरिजिन पकडलेलं आहे. ऑर्डिनेट इज 0 0. So Z is 0, right? So under the load where Z is equal to 0, where Z is equal to 0, where Z is equal to 0, where Z is equal to 0. Next, write down the value of, write down the equation of A beta Z. Write down the equation of A beta Z. So sine 0, sine 0,
0.
sine 0,
0 0
0, cos 0,
1
1, e raised to
1.
0, e raised to 0,
1.
right? So A beta Z is equal to 1. Is it correct? Yes?
yes sir.
Then C beta Z. Again, C beta Z. Again, sine 0, 0, cos 0 is 1, e raised to 0 is 1. So C beta Z is also equal to 1. Okay, so please write down this equation of A beta Z and C beta Z. ते दोनच का? कारण आपल्याला काय विचारलेलं आहे न्यूमेरिकलमध्ये डिफ्लेक्शन आणि मोमेंट. बी आणि सॉरी थीटा आणि व्ही वायची गरज नाही आहे कारण विचारलेलं नाही आहे. We have to find out maximum deflection and maximum bending moment and bending stress. So in the equation of deflection, there is term A beta Z, and in the equation of moment, there is a term C beta Z. So we have considered these two terms only, as in the numerical it is asked about deflection and moment. Right? Write down these two equations of A beta Z, sin beta Z. Then next line, write down these equations of A beta Z and C beta Z. As load, below the load, we have taken at particular point that is called as origin where Z is 0. So for Z0, A beta Z and C beta Z is equal to 1. So next line, around at where Z is equal to 0, A beta Z is equal to C beta Z is equal to 1. A beta Z is equal to C beta Z is equal to 1. Shall I proceed?
Yes sir.
Right. Now we have to find out y, m and stress. Write on the equation of y. Equation of y, write down y max, that is maximum deflection and maximum bending moment below the load. Below the load, so y max or delta max, write down, is equal to p beta by 2k into a beta z. P beta by 2k a beta z. Equation तुम्ही already लिहून घेतला. So put